Hello everyone. Am I audible? Okay. Is the screen visible? Okay, thanks. So let's wait till 6. We will start our session after that. Yeah, so someone actually messaged me that they are facing some issue while uploading the assignment or something, or maybe they missed an assignment. So, for things related to the assignments uploading or any course related stuff, that logistics, so that is being handled by the NPTEL team. So, in case you are facing any issues while accessing the platform or uploading your assignments, please drop them an email. I think that will be better. You can also use the forums to convey those messages, I think. So, um, so that they can take necessary steps to resolve the issue. Okay, I think we can start our session, and meanwhile, the other students can join. So, good evening, everyone. My name is Arpit Bal, and I am a PhD scholar at Department of Electrical Engineering, IIT Bombay. I am the NPTEL PMRF TA for this course, Digital IC Design, and I welcome you all to the sixth live session. Okay, and this live session runs every Tuesday from 6 p.m. to 8 p.m. So, previously in the first week, we did few numericals related to the VTH variation with VSB, that is related to body effect, and we also did few questions related to figuring out the region of operation of NMOS and PMOS. Okay, then drain current equations, using the unified current equation, we figured out what will be the drain current. Okay. In week 2, we did some numerical which also takes into consideration another short channel effect, that is DIBL. Okay, we did some questions related to junction capacitance as well, and we did few numericals on PMOS. In week 3, we did numericals on trip point, numerical on VIH and VIL, and some numerical on calculating the output of a given configuration. Okay. Week 4 was mostly concentrated on this noise margin and Elmore delay. So this Elmore delay, we are going to do few problems today. So that will be using the concepts of Elmore delay. So okay, week 5 we did questions related to dynamic power, delay, and 1 or 2 questions on process variation. Okay, let me check if I have started the recording. Yeah. Okay. So in today's session, what we will be covering is mostly related to again delay. Okay, then electrical effort. Okay, and then given a function, how to get the equivalent CMOS schematic. Okay, consisting of the pull down network as well as the pull up network. Okay, then there will be a few capacitance calculation, and few questions on gate sizing. Okay, so let us start today's session with this brief introduction. So question number 1, so we have a function given f is equal to AC plus BD E whole bar. Okay, so we need to draw the CMOS schematic. Okay, consisting of both the pull down as well as the pull up network. Okay, second thing, we need to size the gates. Appropriately. Okay, third thing, find the rise propagation delay, okay, which is also called as the worst case delay. Okay, so this question will touch more than one concept, so I'll request you to focus on this one. So before starting this question, so I'll suggest you to grab a pen and paper so that you can solve these numericals along with me. So this is not exactly a numerical, but yeah, solve this question along with me. And if you have any doubt at any point, please feel free to interrupt and let me know that there's a problem, because the following questions like that will come up subsequently, that it's going to need question one's concepts that we will be clearing now. Okay, so starting with the first point, so we need to figure out what is the CMOS schematic. So okay, so let me know. So for a pull down network, what should I use? Should I use NMOS or a PMOS?
NMOS.
Yeah, and why is it so?
Because it can completely pass logic 0, or in other words, it can completely discharge a capacitor.
Correct. So let us assume a scenario when I am not using NMOS in the pull down network and I am using NMOS in the pull up network. Then what will be the issue?
It can only, the output will not be pulled completely to VDD, but instead it will only be pulled to VDD minus VTHN.
Correct. Okay, so because of the exact same reason that Prajwal mentioned, so pull down network is going to be using NMOS because it can go completely till 0, and the pull up network will be consisting of PMOS because it can completely go up to VDD. Okay, and if we would have used NMOS in the pull-up network, then the maximum voltage that the V out could have gone is VDD minus VTHM. Okay, so with this brief introduction, let us start. So we have this function given to us. So the first step is to take the complement of the function that is assigned. Okay, so the complement of this thing will be AC plus BD into E. Okay, now let us start with the pull down network. Okay, I'll start drawing the pull down network. So I have A. Okay, then I have an AND operation. So whenever you are drawing an NMOS logic, so if you have an AND operation, it means the other component is in series. Okay, so A dot C plus, so plus will be a parallel B D. Okay, then this complete thing is in series with E. Okay, and let us call this node as F. Okay, so once we have drawn the pull down network, okay, we just need to take the dual of that one to get the pull up network. So what is dual? Basically whatever parallel we have put, we need to convert it into series, and whatever we have kept in series, we need to convert it into parallel. Okay, so it means here we have AC, so AC in series, so we need to convert that AC into parallel in the pull up network. Okay, so let us start with the AC first. Okay, so this is my A. This is my C. Okay, so after AC, what do we have in parallel? We have BD. So BD is in series with parallel to AC. So what will happen is, because of this thing in parallel with this, let me call this network X and Y. Okay, so it will be in series when the dual of this thing is considered. Okay, so we have already drawn X, let's draw Y. Okay, so this is my B, this is my D. Okay, and now what is left in the pull down network that needs to be present in the pull up network, that is E. Okay, so E is actually in series with A dot C plus B dot D. So the dual of that will be a parallel arrangement like this. Okay, and this is connected to VDD. Okay, so I'll pause here for a moment. So let me know if everyone is clear with the CMOS schematic part. Okay, is there anyone who has a doubt here? Okay, okay, so then we can move to the next part, that is sizing the gates. Okay, so before you start sizing the gates, okay, so you just mention the initial value before sizing. Okay, so what will be the initial value for NMOS? That we will assign it to be 1. Okay, but for PMOS it is going to be 2, and the reason for that is because to take into consideration the propagation delay, that PMOS is roughly twice slower than NMOS, so we need to take the width as 2. Okay, so this is the these are the values before sizing the individual MOS. Okay, so now let us start sizing. So the sizing will happen by considering the worst case delay path. Okay, so the worst case path to charge or discharge this particular output node. Okay, so let us start with the pull up network that is consisting of PMOS. Okay, so the worst case will be when let's say this D, C or B and A. So if those two are turned on, okay, so then what we will have two resistors in series. Okay, and we want that two resistors in series, the combination of that should be equal to one resistor. Okay, so to do that, what we are going to do is we are going to increase the width by twice for each of these gates. Okay, by increasing the width to twice, the resistance will become half. So this part will have R by 2 and this part will have R by 2. Okay, so R by 2 plus R by 2 will give us R. Okay, so this 2. Okay, now so whenever I'm using an arrow, it means I'm sizing that gate to some new value. Okay, so this will become 4, this will also become 4. Okay, and if DC is on, then it will mean that the worst case path will be this path, right? So I need to size these two as well, otherwise it will be asymmetric, right? Okay, so do I need to size E? Can someone tell me?
No.
Okay, so E we won't size. E will be kept as such because E is not present in series with something, so it is anyway going to offer you a resistance of R. Okay, so the pull-up network sizing is done. Now moving on to the pull-down network sizing. Okay, now you can see the worst case path will be either this or this. Okay, in which 3 MOSFETs will be in series with each other. So if 3 MOSFETs will be in series with each other, then the series resistance is going to be 3R. Okay, so to counter this, what we will do is we will size each of these MOS by a factor of 3. Okay, so this will become 3, this will become 3, and this will also become 3. Okay, and to ensure symmetry, we are going to size these to 3 as well. Okay, so this ends the sizing part of this question. So is everyone clear about this part, or is there any doubt? Is everyone clear with this part? Okay. Okay, which part should I repeat? Can you mention? So are you clear with the CMOS schematic drawing part? Okay, the pull down network. Okay, so in the pull down network, so the first thing that we need to identify is which path is having more number of transistor stacks. Okay, so you can see, let me call this path from BDE as path 1 and from ACE as path 2. Okay, so in either of these paths we are going to have 3 transistors in series, right? So if we have n number of transistors in series, then it will mean that the resistance of that path is going to increase by n times, correct? But we need to ensure that whatever stacking we have, the resistance is equal to the resistance of a unit inverter, that is 1. Okay, so to do that, what we are going to do is we are going to scale the width by the factor by which we want to reduce the individual resistance. Okay, so because it becomes 3R and we want to make the resistance per the resistance of the entire path to be R, so what we will do is we want to reduce the resistance by a factor of R by 3. Okay, so we will size the individual gates 3 times. Okay, so we have r by 3 plus r by 3 plus r by 3 and it becomes r. Okay, does that answer the question? Is your doubt clear now? Okay. Okay, so is there any other doubt for the gate sizing part? Anyone has any doubt?
So pull-up transistor.
Okay, so pull-up transistor, you can see that, okay, let's call this path as path 3 because I used 1 and 2 already, and this path is path 2. Okay, so in let me call this path as path 4. So in path 3 you can see there is only one MOS that is present, so the resistance that it will be offering is R. Okay, but in path 4 it has to go through at least two MOS transistors, right? So it means it is going to see a resistance that is R plus R, that is 2R. Okay,
Okay.
but I need to ensure that the resistance that is being seen through path 4, it is R. So what I will do is I'll try to double the width of individual MOS so that the resistance becomes R by 2. Okay, and the equivalent resistance of path 4 will also become R.
Okay, sir.
Okay, so initially it was mentioned that the PMOS width we will be taking as 2 because of the mobility, to take into account the mobility factor. Okay, and then we sized it to 4 so that we have an equivalent resistance of R in that particular path. Okay, so that's how the pull-up network was sized.
Okay, sir.
Okay. Okay, so moving on to the third part of the question. So we need to find the rise propagation delay. Okay, so that's basically the worst case delay. So can someone tell me when will be the worst case delay observed?
When both A and B are on, or else C and D are on in
Correct.
PMOS network pull-up.
Yeah. So because it is saying rise, so we will understand that it is going to be in the pull-up network. Okay. Let me write it in a fresh page. So it is rise, so pull up. Okay, and as someone mentioned, that condition is going to occur if the path 4 is followed. Okay, so if okay, let's find the capacitance at this node first.
(16C).
Okay, so let me call this C net. Okay, so C net will be, so just try to observe how many transistors are connected to this node. So we have this transistor, this transistor, this transistor, this one and this one. Okay, so it will be 2C plus 2C plus 2C from the pull-up network plus 3C plus 3C from the pull-down network.
It's 4C. You scaled it to 4.
Oh, sorry, apologies. It's 4C. Okay, so 4C, 4C, 4C plus 3C, 3C, 3C. So we will have...
No, 4C, 4C plus 2C. E is not scaled, it's kept as it is.
Okay. So we have 10C plus 6C. That is 16C. Okay.
So please repeat, sir.
Okay. So are you clear with the sizing of the gate part?
Sir.
Okay. So after sizing the gate, what we do is we are figuring out what is going to be the rise propagation delay. Okay, and to get what is the rise propagation delay, we know that the rise time will depend on your pull up network. Okay, so for that reason what we are going to do is we are figuring out which path is going to contribute to the worst case delay. So that is path 4. Okay, because it is going to going through this, like going through two MOS transistors.
Okay, sir.
Okay, then second thing, okay, so let me make one correction here. So even though it is going through two MOS transistors, because we have sized the gates appropriately, so the path delay for path 4 and path 3 will be same. Okay, so in this case, because we are finding the rise propagation delay after sizing the gates, so it is not going to matter which path you take. Is this point clear?
Yes, sir. Yes, sir.
Okay. Okay. So if I would have mentioned that without sizing the gates appropriately, figure out what is the worst case delay, then you would have said that path 4 is going to have the worst case delay, and that will contribute to the rise propagation delay. Okay, so after doing that, what we need to figure out is what is the capacitance connected to the output node. Okay, so the capacitance connected to the output node will be the capacitance contribution from the pull-up network plus the capacitance contribution from the pull-down network. Okay, so the capacitance contribution from the pull-up network is for this particular node, it is 4C plus 4C plus 2C, then 3C plus 3C. Okay, so let me redraw it. Okay, let us consider this to be R by 2 because it is after sizing. Okay, so I'll tell you which one is R by 2. So let us consider the path 4. Okay, and if this is means the transistor marked in B, that is your that is contributing a resistance of R by 2. Okay, then the next transistor is also contributing R by 2, and this is my output node, okay, which has a capacitance of C net. Okay, so my C net that we found out was 16C. Okay, let me call this node as X. So what will be the capacitance at node X? So this is node X. Okay, so capacitance at node X is 8C. Okay, it's because we have 4.
It's only 4C.
Yeah, no, it will be 8C, right?
It's shared contacted diffusion, right?
Correct.
So,
but we have this B and D both present there.
oh, right. Sorry,
Okay.
yeah.
Yeah. So yeah, as you mentioned, the contacted that diffusion. No. So if we would have a contacted diffusion, then we would have considered it to be 16C. Okay, it is shared non-contacted diffusion. So that's why it is 8C. Is that clear?
Yes, I forgot that C.
Okay.
That's why.
Yeah. Okay, so this is going to be 8C. Fine. Okay, so now we are going to use the Elmore delay to estimate the delay in this particular case. So, okay, so starting with step 1, list down all the capacitance present in the path. Okay, so with 8C, can someone tell me what value of resistance should I put?
R by 2.
Yeah. With 16C, how much should I put?
R.
Yeah. Okay, so we have 4 RC plus 16 RC. So my net delay is 20 RC. Okay, so this is my rise propagation delay. Is everyone clear with this, or is there any doubt? So because this question comprises of several concepts, so it's better if anyone has a doubt, then they clear it now.
So how to get 16C?
Okay, so 16C, okay, so you can see we have this transistor A and transistor C. Okay, and the capacitance is proportional to the size of the device. Okay, so because the size is 4, okay, so I'll say that A is contributing 4C and C is also contributing 4C to this node.
Okay, sir. Okay.
Okay, similarly E is contributing 2C. So we have 4C plus 4C plus 2C for the pull-up network. Okay, and then we consider the pull-down network. So A in the pull-down network is contributing 3C and B is contributing 3C. So we have 10C plus 6C, that is 16.
Okay, sir.
Okay. Is there any other doubt in this question? Okay, so I'll proceed to the next question, or should I pause for 1 minute so that... Should I proceed to question number 2?
Yes, sir.
Okay. Okay, so question number 2 is, we have a logic, okay, this is question 2. We have a logic gate sized for equal rise and fall delay, implements the equation y, okay, a logic gate sized for equal rise and fall delay implements the equation y equals to a plus b plus c whole bar. Okay, where y is the output of the logic gate and a, b, c are the inputs to logic gate. The sizes of the PMOS and NMOS connected to input C respectively are dash and dash. Okay, so you have to figure out what is this. So give it a try. I'll wait for 1 minute because this is similar to the question that we did just previously. So can someone tell me what should I do first? So I have a function given to me. Okay, so how should I go about solving this question?
The schematic.
Yeah, so first thing is we will draw the schematic. Okay, so to draw the schematic, what are we going to do first? Should I go with the pull down network first or the pull up network first?
Pull down.
Yeah, so we can go with any either pull down or pull up, but it is easier to do the pull down network first and then we will take the dual of the pull down network, that will be our pull up network. So whenever you are given to design a CMOS circuit, so try to follow this step, so that will be easier. Okay, so let's start with the pull down network. So we have y is equal to a plus b plus c whole bar. So y bar will be a plus b plus c. Okay, so how does the pull down network look? Can someone just verbally mention?
3 parallel B and C transistors in parallel.
Correct. Okay, so we will just put 3 transistors in parallel, A, B, C. Okay, so what will be the dual of this network?
Series.
Okay. Okay, So the next thing that we are going to do is we will size them. Okay, so this is the value without sizing. So let me know after sizing what will be the value of individual MOS.
And MOS will be 1 and PMOS will be 6.
Okay, so for all the ABC transistors.
Yes, sir.
Okay. Okay. Yeah, that's correct. That so for NMOS everything will be 1. So we are not going to size it further, because the worst case path is any one of the NMOS is on. Okay. So at that moment we will be having resistance R. But in case of PMOS, when all three are on, so we are going to have a path having a series resistance of 3R. So we need to size it by 3 times. So initially to reduce the resistance of each MOS by a factor of 3. So initially the width was 2. So now we are going to make it 3 times wider, that is going to be 666. Okay, so the answer to this question is PMOS is going to be 6 and NMOS is going to be 1. Okay, is this part clear?
The question is actually not clear. They have mentioned a logic gate sized for equal rise and fall delay. But even if we size them according to whatever is mentioned, we won't get equal rise and fall delay.
Okay, why not?
Fall delay will be like if we consider fall propagation, it will be 9 RC, whereas if we consider rise propagation, it will be 15 RC. No matter what we do, they both won't be equal. The question should be, it should be sized in reference with a reference inverter.
Oh, okay. Yeah, actually, if you have gone through the last lecture, so what they do is, instead of going through the classical Elmore delay method in which we take into consideration each and every node, okay, so we just take the output node's capacitance. Okay, so if we just take the output node's capacitance, then this one becomes RC and this one also becomes RC, right?
Yeah, okay. If we ignore the intermediate capacitance,
correct. Yeah. So yeah, this question, okay, so this assumption should be also mentioned. I'll mention this then. Ignore intermediate node caps. Okay. Okay, so moving on to the next question. So we are given a function. So this is a bar. Okay, it means whatever this function is implementing, you need to take the complement of that. Okay, and you have a sum of product. You need to come up with the sum of product expression. Okay, so 0723. So this is a digital electronics question. So can someone tell me what is the number of bits that I need to implement this function?
3 bits.
Okay. So how do you figure out how many bits you need to implement a particular function if you know what minterms are going to be present?
Taking log to the base the maximum.
Yeah. So log to the log of base 2, log base 2 of the maximum minterm value that is present here. Okay, so if let's say it would have written M0 1223, okay, then so okay, so you take the seal of this function. Okay, that will give you the minimum number of bits needed to represent a function. So because in this case the maximum value is 7, okay, then it means that it can be represented with 2 point some xyz bits, that translates to 3 bits. The ceiling of that will be 3 bits. Okay, so I can write it like this: ABC. Okay, I'll draw the key now. Zero 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 one one zero three six seven 5. Okay, 0723. So what I am implementing now is, let me call this sum x is equal to summation of m 0723. Okay, so I have 0 here, 7 here, 2 here, 3 here. Okay, so let us read the question completely. So what is the size of NMOS stack required to implement this following function, where mi is the ith minterm? You may assume that there are only as many inputs to the logic gate as are left after logic reduction. Okay, so this statement is very important. Second statement, you may also assume that both true and complement versions of the inputs are available. Okay, so do not go about using an inverter to get a bar from a. Okay, because it is already mentioned that both true and complement versions of the inputs are available to you. Okay, so because this logic reduction thing is mentioned, so without directly writing 0723 as a bar, b bar, c bar plus abc plus a bar, b, c bar and all, so we are going to do the logic reduction first. Okay, so I use a K-map. So I'll just encircle the adjacent ones. Okay, so this adjacent ones will give me BC. This adjacent one group will give me a bar B, and this adjacent one group will give me a bar C bar. So my X becomes a bar C bar plus a bar B plus BC, but my F is given as summation of M 0723 ka whole bar. So that is a bar C bar plus a bar B plus BC ka whole bar. Okay, is everyone clear till this step? So this is only basic digital electronics, but yeah.
And actually, our doubt. The A bar B, it's already covered in A bar, C bar, and BC, right? We don't have to group that
Correct.
cells 2 and 3 together.
Correct. Yeah, so you can only take two terms as well. A bar, you can ignore A bar B. The answer will remain same.
Okay.
Wait, someone is trying to join. Okay. Yeah, so after the logic reduction, yeah, is there any question, Dindal?
Yes, sir. It's more simplified than the X node will be the BC plus A complement, C complement.
Correct, yeah. So actually that's the question that Prajwal asked. So we can ignore this particular term. Yeah, okay, let's ignore it. A bar C bar plus BC, because all the minterms are being covered by these two circles itself. Okay, so so from this function itself, can you tell like how many what is the size of the NMOS stack required?
2.
Yeah.
No, 3.
Why?
It will be 2.
Yeah, it will be 2. So why was it 3? Someone mentioned 3.
There are 3 inputs total, A, B, and C, and they were told that assume as many inputs to the logic gate as they are left after logic reduction.
Yeah, but so here we wanted to know what is the size of the NMOS stack. So when we say stack, it means how many NMOS are in series.
Oh, right, yeah.
Okay, So that's why it is going to be 2. Let me add one more slide here. So okay, so let me draw this so that it will be clear. So what is the value? A bar C bar plus BC. Okay, and this is the PDN. So I have A bar, I have C bar, I have B, I have C. Okay, so the maximum number of NMOS transistors present between the output and the the ground node, it is 2, right? So because of this reason, the stacking of NMOS, the size of stacking is 2. Does anyone have any question in this one? Okay, so we moved from this to this because A bar B is redundant, because A bar C bar and BC is actually taking into consideration all the min terms. Okay, is everyone clear about this question? Okay. Okay, so moving on to question 4. Okay, so is it same question? No. Okay, so this is a different question. So what is the size of NMOS stack required to implement the following SOP? Okay, so here this particular function is given different. Okay, so let us start. Let me call this X. So X is equal to summation of 0, 1, 4, 7. Okay, and we have this after logic reduction part, and both true and complement version is available part. Okay, so again the maximum value is 7, so the number of bits needed will be 3, number of inputs needed. Okay, then I'll write it 0, 0, 0, 1, 1, 1, 1, 0. Okay, this one is 0, 1. Okay, this is 0, this is 1, this is 2, this is 3, this is 6, this is 7, this is 4, this is 5. Okay, so let us mark 0, 1, 4, 7, 0, 1, 4, 7. Okay, so I can group this, I can group this, and this will be left alone. Okay, so can someone tell me what are the min terms after reduction? What is this?
A bar, B bar.
Correct. What is this?
ABC.
And what is this?
C bar, B bar.
Okay, so can it be reduced further? Yeah. Okay, so this is the final expression that we have for X. So X is equal to A bar B bar plus ABC plus B bar C bar. Okay, so my F becomes A bar B bar plus ABC plus B bar C bar ka whole bar. Okay, because there's a bar over here. So can someone tell me what is going to be the stack in
3.
this case? Yeah,
3.
correct. Okay, so did you observe any pattern by which you can directly say that the stacking of NMOS is going to be 3 or some other number? Or do you need to draw the schematic for that?
No, A, B, C, A and with B and with C, so all of them will be in series. That is the maximum possible
Correct.
stack size.
Correct. Yeah. So to figure out what is the maximum possible stack of NMOS, you see the AND related terms, right? So if you see an AND term, because we have already done the logic reduction here, so the number of terms present in the maximum ANDed value, so that is going to be your maximum NMOS stack size. Okay, is everyone clear about this question, or is there any query? Okay. Okay, so we will move to the next question. Question number 5. Okay, so we are given the sum of the sizes of the PMOS transistor of the logic gate that is shown above. Okay, so what is the worst case pull up and pull down resistance? Wait. Okay, yeah, so that the worst case pull up and pull down resistance is identical to that of reference CMOS inverter. Okay, so reference CMOS inverter is something like this. Okay, and you need to ensure that you are sizing this network so that the sum of so that the worst case pull up or pull down resistance, it is identical to that of reference CMOS. So here we can only consider about the pull up part, because we are asked to get the sum of sizes of PMOS transistor. So can someone tell me?
14.
Okay, and how did you come up with this number?
A is sized 2,
Okay.
B, C, D 4.
Sized 4.
Okay, like this.
Yes.
Okay.
Yes.
And so can you again mention why this PMOS number was 2?
So that the path resistance become R.
Yeah, that's correct. But why is NMOS 1 and PMOS 2?
Because of the mobility, we have to take it into consideration.
Yeah. Okay. So the summation of all the sizes will be 2 plus 4 plus 4 plus 4. That is 14. Okay. Is everyone clear with this part, or is there any doubt? Okay, there's a message. Yes. Oh, okay. Okay. Okay, so we will proceed with the next question. Okay, so now it is asking for the sum of sizes of NMOS transistor. So PMOS transistor was shown, but NMOS transistor isn't shown. So we need to first figure out the dual of the PMOS transistor. Okay, so let us start drawing that one. Okay, so here A is in parallel with this network. So in the pull down network, the dual of that will be A in series with this complete network. Okay, now let us start breaking down this network. So B is in series with this couple. Okay, so B, so the dual will be B in parallel with DC couple. Okay, and DC are present in parallel, so it will be DC in series. Okay, now let us start joining the dots. So B in parallel with DC couple, so we will have B in parallel with D and C in series. Sorry, this is not proper. Okay, is everyone clear about this construction? Taking the dual of PMOS. Okay, so now the thing is, we need to size it appropriately so that we have the worst case pull up and pull down resistance identical to the reference CMOS inverter. So reference CMOS inverter, I drew it in the previous slide, previous question. Okay, so can someone tell me, okay, so let me call this as path 1. Okay, so does everyone agree that path 1 is the path that is going to give me critical delay?
Yes.
Okay. A2, B2, C4, C equal to D equal to 4. Okay, let's see. Okay, so can someone tell me how should I size A, D and C?
All will be
Size
sized
will
by
be
3.
3.
Okay. Okay. So if I size everything with 3, then the resistance of path 1 becomes R. Okay. So how should I size B? Let me call the factor by which I need to
3
scale
by
it.
2.
Yeah. So let me call this as X. So if I consider the path 2, the resistance of path 2 should be R as well, right? So I have R by 3 contribution from A plus R by X. So if you scale any transistor by a factor of X, then the resistance drops by a factor of X. Okay, so this is path 2. Okay, and this should be equal to R. So we have XR plus 3R equal to 3XR. Okay, 3XR and XR, it will be 2XR. So we have 3R is equal to 2XR. So we have X is equal to 3 by 2. Okay, so my B transistor will have sizing factor of 1.5. Okay, so the sum of sizes is equal to 3 plus 3 plus 3 plus 1.5. That is 9 plus 1.5 equals to 10.5. Okay.
Sir, one question.
Yeah.
Sir, why can it will be sizes in 2 and 4? Because only in integers.
Okay, you want to size it in integers? Yeah, sure. So you want to so what value do you suggest?
Sir, in case of both A part and another the complex part, it will be cascaded, so it will be sizes in double, so 2, 2, and what parallel it should be in same size. So B should be in 2, and the C and D share will be equal, so it will be 4, 4, as mentioned in this lecture of also.
Sorry, I didn't get that part. Can you repeat once again?
Sir, the A part, A transistor part, and the CD and B transistor is another complex part. I assume that. So A part and this part is in series. So A part have a double size of width, and that next complex part will be in double in size. So both B and CD are in parallel. So B should be in 2 and C or D should be in 4, 4.
No, right? Because okay.
He's saying that if D and C are scaled by 4, then resistances will be R by 4 and R by 4 respectively for both D and C.
Correct.
So it will be R by 2, and B, if you size it by 2, it will be R by 2 as well. So he's saying A will be sized by 2, so net resistance in both the parts will be R. But sir said that in the lecture we can't do that.
Yes.
It will result in more area.
Correct. Yeah. So our objective is to let us assume that what Saugata mentioned. So you are saying this is 2, this is 4. Okay, I'm putting it in circle. This is 4 and this is 2 as well. Is that what you mentioned, Saugata?
Yes, sir.
Okay. So let us see the summation of widths here in your case. So the summation of widths will be 2 plus 2 plus 4 plus 4. Right? that will be 6 plus 6, that is going to be 12. Correct?
Yes.
But if we size it like 3, 3, 3 and x equals to 1.5, then the summation of widths will be 10.5. Okay.
Sir, can you explain me in 3 how we find the value of 3?
Okay.
1 second.
So the first step that we do is we figure out what is the critical path. Okay. And the critical path will be the path which is having more number of transistors in a stack. Okay. So here we see the more number of transistors in a stack wala path is this path. Path 1. Okay. When it passes through A, D and C.
Yes, sir.
Okay.
Yes.
So the first step that we do is we will size that path. Okay. So if A, D and C is present, so it means that there are 3 series resistance. So from 3 series resistance, I need to get an equivalent resistance of R. It means I'll size everything by a factor of 3. Is that clear? So that's my first step.
Okay, sir.
Okay. So after I size A, D and C that is present in the critical path by a factor of 3, so the remaining transistor, okay, so how much should I scale it? So that this path that I am calling as path 2, okay, so if A, B is present, then that path should also give me a equivalent resistance of R. Okay, so for that reason I have already sized A, so that is giving me R by 3. Let me size B by a factor of X. So that will give me a resistance of R by X. And these two are in series, so I'll add them up. And the equivalent should be R. Okay, then solving the equation, I'll find out what is the value of X.
Okay, sir. Understood.
Okay. Yeah. Is there any other question? Like, does anyone have any other question in this particular numerical? Okay, so if asymmetrical stacking is present, then you can use this method to figure out what should be the appropriate sizing. So this is a very important question. So
sir, for solving this question, we should always go for the optimum area. That means for this step.
Yeah.
By using X and finding
Yeah.
Go for the critical path delay.
Yeah. So always start with the critical path first. Okay. Any problem you solve, you start with the critical path first. Then you try to figure out what is the missing pieces in that puzzle. Okay. So is everyone clear with this question? Is there anyone who has any doubt? Okay. Okay, once again, should I explain? Okay. Yeah, so the question was, so we needed to design, so we needed to figure out what is the sum of sizes of NMOS transistor. So the first thing that we did is, we are already given the PMOS transistor, we take the dual of that to get the NMOS. Is that part clear? Okay, so after we got the schematic for the NMOS, the pull down network, we first try to figure out what is the critical path. Okay, and the critical path is the one which has the highest number of transistors stacked. Okay, so do you agree that path 1 is critical? So I am calling the path from A, D and C as the critical path. Okay, so after you have figured out the critical path, what you do is you size the transistors appropriately, so the critical path will give you an equivalent resistance of R. Okay, is that fine? Okay, so after sizing A, D and C, so these sizes are fixed, we are not going to touch it ever. Okay, then we see what transistor is not sized, so that is transistor B. Okay, then what we do is, so bring your focus to this section. So what we do is, so let us say that I am scaling B by a factor of X. So any transistor, if I scale it by a factor of X, it means the resistance is going to drop by a factor of X, right? So A and B are in series, okay, and I'm calling that as path 2. Okay, and my path 2 should also offer the same resistance, that is R. So I have R by 3 plus R by X is equal to R. Okay, so after writing this equation, the equation 1, I solve for X. Okay, so I get the value of X is equal to 3 by 2. It means if I have B with a scaling factor of 3 by 2, then path 1 will give me same resistance as path 2, that is equal to R. Is that clear?
Sir, the same concept is also valid for the PMOS style, right?
Yeah, sure.
Okay, sir.
So for PMOS we don't have any asymmetrical path, okay, because you can see that so PMOS, which transistor do you have? Are you suspecting that it can have that X wala factor?
No, sir, the critical path should be in the highest stack, so it should be in BD or BC, both same. No?
Correct. So that's why BD and BC we have kept it same. That is 4-4, and this is also 4-4.
Okay, sir.
Okay, so question number 7. So we need to find out. So for question 3, will the answer be same if there is no complement for the minterms given? No. So if no complement for the minterm is given, it will mean that you need to generate the complements. Okay, but usually I don't think you need. Okay, let me go to question 3. Okay, so here if this assumption is not present, it means you need to generate the complements. It will mean that those things should pass through a CMOS inverter. Okay, and it is going to further complicate the question, but I don't think that thing is going to be asked to you. So you can easily assume, no, don't assume, so it will be given to you that both true and complement versions are present mostly. Okay, so for question number 7, we need to figure out what is the diffusion capacitance on the output node of a NAND 4 gate. Okay, so let us start. Yeah, is there any question?
No question.
Okay, so we will start with the pull down network. So it is NAND, so it means it will have something like A dot, B dot, C dot, D whole bar. Okay, so my NMOS stack will look something like this. Okay, and my PMOS stack will look something like this, because everything is in series, so the dual will be everything in parallel. Okay, this is my VDD and this is my VSS or ground. Okay, and this is my output node. Okay, so tell me the sizes for each transistor.
2 for all the PMOS, 4 for all the NMOS.
Okay, 4 for all the NMOS and 2 for all the PMOS. Okay, so what will be my C net here?
12C.
Yeah. So how is it 12C?
2C from each of the 4 PMOS transistors and 1 4C from a NMOS transistor.
No. The answer is correct, but there won't be individual contribution of 4C from each PMOS, right? It will be
No, 2C from all 4 of the PMOS.
Oh, okay.
So
okay.
8C in
Yeah,
total.
correct. Yeah. Okay, so we have 8C plus 4C from the NMOS that is directly connected here. Okay, so that will be 12C. Okay, so the K value is 12. Okay, is this question clear? Okay, so question number 8. Okay, so question number 8 is going to be question number 1's fall propagation delay. Okay, so we
16
will.
RC.
Okay, that was quick. Yeah, and why could you say it 16 RC so quick?
Because anyways it will be R in the bottom stack, and
Correct.
I already remembered it was 16C when we
Yeah.
had short, so I just multiplied.
Yeah, that's correct. Because we anyways tried to make the equivalent resistances R for both the networks. Okay, and we need not find the C net again. Okay, yeah. So that was the tick question part. But yeah. Okay, so there will be another question number 9. Okay, so for question number 9, so let me call this as G. As H and receptic effort as P. Okay. Size 1 logic gate. Okay, so GHP is the logical effort, electrical effort and parasitic effort for size 1 logic gate. Okay, okay, you need to figure out what will be the electrical effort for size 4 logic gate. Can someone first define what is electrical effort in terms of maybe the abbreviations CL and something?
CL by CDUT.
Okay. CL by CDUT. Okay. So when it says that we are moving from size 1 to size 4, is the CL going to change?
No.
Okay. So is the CDUT going to change?
Yes.
Okay. So what will be my new CL by CDUT?
1/4.
Yeah. So this will be 1/4, and because CL by CDUT given for size 1 is H. Okay, so this is 1/4 H, this is 0.25 H. Okay, so yeah, I think there was one more question. Where did it go? Okay, there is one more question. Just give me a moment. Okay, so we will have. Okay, there is some question. Any change in logical effort? No.
Yes. It will change.
But it will depend on the number of inputs that is present, right? Logical effort does only depends on topology.
Yeah, if we are making it size 4, then topology will be complicated, and hence definitely by definition logical effort should increase even without the calculations.
Oh, sir, I think logical effort won't change. Topology won't change.
Yeah. So unless the topology
That's just
changes.
scaling.
Correct.
Oh, right. Size 4, they are just scaling
Yeah.
without number of inputs.
No,
So, yeah.
number of inputs won't. And yeah, there is. Yeah, so it is not going to change. Does that answer your question, Vaibhav? So logical effort is something that is purely due to the topology of the gate. So unless the logic changes, like if it is changing from A dot B to A dot B dot C or something, then only the logical effort will change. Yeah, I actually upload the recordings by 8:30 mostly. Like it doesn't take much time. I think. Yeah, so I upload it on this thing, and yeah, so it will be uploaded by 8:30 or 8:45. So don't worry about that. Then yeah, just one more question left. So question 12. Where did it go? Okay. So we have a function is equal to this. Okay, so I want you guys to try to solve this question. So just figure out what is the sum of NMOS sizes. Okay, so please try to do this question.
10.5.
10.5.
Okay, I'll wait for others. Was this question done in the class or something?
Yes, previously we have solved it.
Oh, okay. Yeah, so for others, they can Oh, okay. I think this was taken up as an example in the class, is it?
Yeah.
Okay. Okay, so yeah, and here I think he mentioned that that particular W will be 1.5. The scaling factor will be 1.5 for one transistor.
Yes.
Oh, okay. Okay, so yeah, these were the questions. What's the answer if complement is not given? For which question? Rishendra? Question 10. Oh, yeah, you need to do it like so. You just let's say f is given as a plus bc into d. Okay, then the first thing is you take the f bar of that one. Okay, but this looks a bit complicated to be done in the NMOS itself. So better try to reduce it further using De Morgan's law. Okay, and once you reduce it, yeah, Prajal.
We can just add an inverter, right? So we'll just add one more.
Yeah,
size,
from the function
11.5
output you can, yeah, correct. So like whatever function you have implemented like this, so what you can do is you can take an inverter and like change the output. Otherwise, if you want to solve it from the function itself, you can go on using the De Morgan's law and figure it out. Does that answer your question? If min terms like 11, 12, 13, it means 4 bits. Yeah. Because to represent 13, okay, so I mentioned some formula, right? So you just take log base 2 of the maximum number. So in this case it is 13, and you take the ceiling of that one. Okay, so the this thing will end up with 4 bits. What will be the size of NMOS stack without complement? Will it change? No, the size of NMOS stack is going to remain same. Okay, so you have mentioned NMOS stack. So if you would have asked sizes of the individual NMOS, then probably yes, it can change. But size of NMOS stack means the number of transistors, number of NMOS in a given stack. That will. Can you explain how 10.5 is coming? Okay, so I'll solve this then. So first thing is draw the schematic. So the schematic looks something like this. So we have A, and this will be your B dot C, right? Yeah, so this is B dot C, and we have A plus B dot C dot D. Okay, this is your D. So the critical path is this path. So it will be thrice 3, 3, 3. Okay, and if I consider this to be X, or to be sized by X, then I have R by X for this path, that is path 2, plus R by 3. Can we conclude that size of, okay, let me complete this one, is equal to R. So we figure out what is X, then X will be 1.5. Okay, so if X is 1.5, then we have total sum of sizes of all the NMOS as 10.5. Is that clear, Vaibhav? Yeah, okay. Yeah, Rishendra, can we conclude that size of NMOS stack will remain same for any function and its complement?
No, sir. It will change.
Yeah, actually it can change. Means so if you are okay, so let us consider this function. Okay, so this is my pull down network. So one of the way to get the complement of this thing is like you put an inverter here. Okay, and you get the complement of that function. No, I think no, you can't conclude this for all the cases, but
Sir, we are introducing additional transistors. Logic itself is changing.
yeah, we are introducing additional transistors, but from output node till the ground point. No, I think yeah, we can conclude that the size of NMOS stack will remain same for any function and its complement. Right, because the transistors in a stack, it is going to remain same, right? The number of transistors in series.
Sir, no, we are introducing an inverter, no sir.
Yeah, but
it should
the
change.
no, because the output of this thing is being applied to the gate of the inverter, so the stacking is not going to change.
If we take output from that point, then logic remains same. We are not considering the complement part of it.
Yeah, but even if we are considering the complement part, then it is not going to go through the source drain part. It is going through the gate part. Right. So stacking is considered when like the transistors are present in series. Is that clear, Ankit?
Okay, sir.
So it is going to be 3, right, Rishendra? So you can see the critical path has 3 transistors, B, C and D. Yeah, if the function is constant, then you can use reference inverter for inverting the function. That is not an issue. But maybe you will need a different drive strength. So not necessarily the reference inverter can be used directly. So maybe you would like to scale it up as per the drive requirements. So that's something complicated that will come later. But yeah. So
In this path, the critical path relay BCD, so the stack should be in 3 because maximum transistors are connected in series. Right?
yes.
That's like.
Yeah.
Okay, sir. Okay, sir.
Okay. So is there any other question?
Sir, regarding the question when you said without the complement and with the complement, the size of the stack should remain same. If you consider the example which is shown in the slide, like A plus B, C to D. So we have calculated with the complement, the size is getting 3. But if we complement it and use De Morgan's law without putting an inverter in the second stage and applying De Morgan's law in that itself, the complement of complement, and use De Morgan's law, then the answer is coming 2.
Yeah, if you are going to use De Morgan's law, means if you are going to change in the function itself, then the stacking is going to change. But if you are simply going to connect an inverter at the output, then the stacking will remain same, right?
Okay, sir.
Yeah. Stacking, the size of the stacks, not the individual size of MOSFETs. Yeah. Okay. So yeah, regarding folks who were asking question about like uploading the slides and all, so the slides will be uploaded. Like you can check on the sheet, that Excel sheet that NPTEL team provided, and the recording like I'll start uploading once this session is over. So it hardly takes around 45 minutes to get completely uploaded. So even that will be available by 8:30, 8:45 at max. Yeah. So that's what. Okay, so we will revisit what we did today. Okay, so in the first question, what we did is, so this question comprises of three concepts. One is getting the CMOS schematic. Second thing is sizing the gates appropriately. Third thing is the rise propagation delay. Okay, so first we draw the PDN. Okay, the pull down network that is comprising of NMOS. Okay, so we take the invert of the function that is given to us, and if two transistors are in are ANDed, then we use the we put them in series. If they have a plus sign in between, then we put them in parallel for NMOS. Okay, and once the pull down network is done, to get the pull up network, we just take the dual of that. So what do you mean by dual? You change the transistors that are put in parallel to series and series to parallel. Okay, so that's how we come up with the CMOS schematic. Then after that, we have to size the gates. So for gate sizing, we figure out what is the critical path first. Okay, so critical path will determine what will be the maximum resistance to that path, and accordingly we will size the gate so that our resistance is equal to the reference inverter's resistance, that is equal to R. Okay, so in this case, let us only look at the pull down network first. So there are BDE, so this forms the critical path. Symmetrically we have ACE that forms the critical path, that is having 3 transistors in series. So the resistance is thrice. So to reduce the resistance, the equivalent resistance of that path to R, what we do is we scale them up by a factor of 3. So if we scale any inverter by a any transistor by a factor of 3, then the resistance drops by a factor of 3. So we have R by 3, R by 3, R by 3 in series, that will be R. Okay, that's how we do the sizing for the pull-up network as well. After the sizing was done, we were supposed to figure out the rise propagation delay. So we just take the critical path, we figure out what is the output node capacitance. Okay, after figuring out the output node capacitance and the critical path, so we just draw the equivalent circuit and we calculate the Elmore delay. Okay, the
Sir,
next,
sir, I have a doubt regarding last question. We calculated the output capacitance as 16C.
Yeah.
Then at point X, it is coming 8C. How that 8C is coming?
Okay, so the point X, which is marked here, so that will have capacitance coming from transistor A, C and BD, right?
Yes, sir.
And the regions of transistor AC and region of transistor BD is overlapped. So we can take either AC or BD's capacitance at point X.
So what do you mean by the region is getting overlapped?
Okay, so so do you remember in the lecture, sir drew the transistor something like this?
Yes, sir.
Okay, so it means it is sharing something common. It can be either a source sharing or a drain sharing.
Okay, sir.
Okay, so in that case, the capacitance that you are considering is going to be like 1 for one of the value, not both.
Okay, sir.
Okay, so what is the contribution at point X because of the B and D transistors?
4 plus 4 equals to 8.
Yeah. Okay, so that's why we have 8C here.
Okay, sir.
Okay, so and once you have this network, equivalent network, you can go on doing the Elmore delay calculation part.
Yes.
Okay, so the next question was regarding gate sizing, and we have already done the gate sizing in question 1. So this was a bit of cakewalk, and we had to figure out what is the size, that is 6 and 1. Okay, so in the next question, we were given a function, and we were supposed to figure out what is the size of the NMOS stack. So yeah, be careful about the size part. So when it is asking for the size of stack, it is asking you the number of NMOS transistors present in series. Okay, and when it is asking you the sum of sizes of individual NMOS, it means you need to sum up the widths, the final scaling factors of the NMOS. Okay, so yeah, and we observed one thing, that if in the final equation we have n number of inputs that are ANDed together in an NMOS, then it means the stacking is n. Okay, question 4 is a modification of question 1. So just to get a bigger logic, so that you can observe that how many transistors are going to be in a stack. So question 5, we figured out what is the sum of sizes of PMOS transistors, so that the worst case pull-up resistance is identical to that of CMOS, reference CMOS inverter, and this is the reference CMOS inverter that is given. Okay, question 6, we were asked to do the same thing for NMOS, but NMOS diagram was not given, so we figured out by taking the dual of the PMOS network that is given to us, and we try to do the sizing. So here we see one more thing. So while sizing, so the first thing that we need to do is size the critical path. Okay, after sizing the critical path, whatever is left, try to include that path such that the equivalent resistance through that path is equal to R. Okay, so that's what we did, and path 2 we tried to equate it to R, and we figured out what is the scale value for D. Okay, question 7 was related to the diffusion capacitance on output node of NAND 4. So we just draw the schematic of NAND 4, figure out what is the individual contribution of capacitance at output node, and that will give us the output node capacitance. Okay, then question 9 was related to electrical effort, where we are supposed to find out what is the electrical effort for a size 4 logic gate. If the size 1 logic gate is denoted as H, then the size 4 will be 0.25 times H. Okay, so these were the questions that I planned for today. If anyone has any doubt, please let me know. Okay, and this particular session will be uploaded on the YouTube channel by 8:30, 8:45. Yeah, so if there is any doubt, then let me know. Okay, yeah, Manav.
So, in this question only, if the question asks about what is the change in parasitic effort.
What? Wait, is it an assignment question or something?
Yeah, it is an assignment question.
Yeah, man, don't do this. Okay, I can't discuss the assignment question, so. Okay, is there any other question apart from the questions asked in the assignment? Okay, so okay, if f is equal to 1, we don't need to use question 9 once more. Yeah, sure. If f is equal to 1, then we don't need to use any transistor, right? So from f is equal to 1, do you mean to say the function is 1 always? Yeah, if the function is 1, then you can take the output from VDD itself, right? Means you don't need to use any transistor. Okay. Question 9 one more time, please. Okay. Yeah, so question 9, we were supposed to figure out what is the electrical effort for size 4 logic gate. Okay, size 1 logic gate's value is mentioned here. Okay, and by definition, electrical effort is your CL by CDUT. Okay, for size 4 logic gate, so your drive strength increases by 4 times, okay, but the CL is not going to change, right? So you can directly write it as CL by 4 times C dut, and we know that CL by C dut is your H, okay, that is already given to us. So that becomes 1 by 4 times H, that is 0.25 H. Okay, so is there any other question? Anyone has any other question? So the submission deadline for the next assignment is tomorrow, is it?
Yes.
Okay. Okay, so if no one else has any doubt, then we can wrap up today's session. So yeah, thanks everyone for joining. So I'll still be here around for some time. If anyone has any doubt, then let me know. Okay, yeah. Thanks everyone.
Sir, for fall time delay, we have to do the same process we have applied for the PMOS in the rise time delay, right?
Yes. So for fall time, you have to do it in the NMOS.
Yes, for the NMOS.
Yeah.
Okay, sir. Thank you.
Yeah, sure.
So if we have something questions with the assignment solutions, or if we think the assignments answers are wrong,
Huh.
then where can we post it or ask?
NPTEL forum is there. So wait, let me open it. Okay, it's not opening for me. So in NPTEL, the Swayam platform, so there is an option called forum, right?
Okay, sir.
So you can post the questions there, then the NPTEL team, which is looking into the assignment part, so they will get back to you.
Okay, sir.
Okay.